So now we are going to look at the stabilization methods with which we can suppress the spurious oscillations in the solution obtained with the finite element method for advection dominated problems. Okay, just to recap, so if you have a very small viscous, sorry, the diffusion coefficient, and if the mesh is not fine enough, we get spurious oscillations in the solution. So to suppress this, we need the stabilization methods. There are a variety of stabilization methods that have been proposed over the years. Okay, so among them, there is streamline upwind petrorelating method, which is one of the quite popular methods in the stabilization methods for advection dominated flows. And Galerkin square method, which is another stabilization method. There is a subgrid stage stabilization, and there is also a stabilization based on the bubble functions, and there is a versatile stabilization based on variation multiscale method. So this is called variation multiscale stabilization, which we use even for turbulent flows. So it's really a quite powerful method. And there are other methods such as finite incremental calculus. So you can learn more about most of these methods from the textbooks, after this lecture, after this course. So please, for the fundamentals of the SUPG method and the Galerkin square method, okay, which we cover in this lesson. So you refer to the textbook I suggested, that is by Donian Huyetta, and also the textbook by Rajiv Jayman. Okay, and there are also a lot of papers published by Professor Tom Hughes and Professor Typhon Tejduar, and also Professor Raman Kodina and their co-authors. Okay, so you can get these papers like by going through, like there are references to these papers in the textbook by Donia and Huerta, so we can get those papers. Okay, right. Okay, so how do the stabilization methods work? What do we do? Okay, so we have looked at the weight form without stabilization. So the standard Galerkin formulation. Okay, this is our weight form, the weight form by following the Galerkin method. Right. Okay. So not by sorry, this is the weight form that we obtained using the weighted residual method, not the Galerkin method. Okay. So and on top of this, we add the stabilization term. Okay. So we add the stabilization term at element level. Now notice the difference here. Now in the standard weight form, we have the integral over the whole domain x, like our coordinate is x, the integral is over the whole domain. Whereas in the stabilization term, our integral is over each element omega e, and we sum over all the elements. Okay, so this is what we do in the stabilization method. Now here again our RU is RU is the familiar to us, which is the residual of the PDE. Okay, and P of W is an operator on the weight function. W is our weight function. P of W is an operator on the weight function. And here tau is the stabilization parameter. Okay, so like I said, stabilization is applied element wise. And because of this, like tau need not be continuous across the elements. Okay, so we can calculate tau element wise, and that's what we will do. So that's what makes this method quite powerful. Okay, so now what is PW? We know RU, this is the residual of the PDE, and tau is a constant with which we calculate element wise and even gross point wise. And the only thing that we don't know is P of W. So this the choice of P of W dictates the stabilization method. So that is for different stabilization method. For example, for SUPG, we have one P of W, and for GLS, we take another P of W, like, okay. So in SUPG, which is streamline upwind petrodilating method, our P of W is only the convection term, not the advection term. Okay, P of W is A dou W by dou X. So this is the convection operator, right? Okay, on W. And in the case of GLS, that is Delaunay least square method, our P of W is the PDE without the source term, without the force term F. Okay. So on W. Okay. So this is the general term for any problem. However, as we know, as we have a second order term here, second order derivative here. Okay. So this derivative becomes zero if we use linear elements. If we use a two-noded element which have linear basis functions, when we discretize this is zero, because for linear elements second derivative is zero. So in this particular case of linear elements where the second derivative is zero, both SUPG and GLS methods become identical. They are identical. Okay. So we can say, like, for linear elements, we can say we are using SUPG or we are using GLS. It's all the same. But for higher order elements, for which the second derivatives do exist, so these methods differ in the higher order terms. Okay. So this is the uh, so SUPG and GLS stabilization methods. Okay. Now we are going to treat as though we are implementing the SUPG method, because it is one of the widely used methods as opposed to the GLS method. Okay. So we have seen like what our P of W is. Okay. So by using it, and we can write the stabilization term. Okay. So we can expand the stabilization term. Okay. Element wise. Okay. We know the integral is from x1 to x2. Okay. So P of W tau RU dx. So P of W is A dou W by dou x tau tau, and RU is A dou U by dou x minus F. Since we are going to use linear elements, we are ignoring the second derivative in the PDE as well. Okay. So note here that we are not going to use the integration by parts and transfer the derivatives. We did that in the original, we did that in the original weak form. But here we already have a derivative on W. So we are not going to transfer the derivatives from U to W again. And since we don't do that, and since the second derivative exists in the PDE of the advection diffusion equation, that is the diffusion term, and since we use linear elements for which the second derivative is zero, we are ignoring the second derivative in the stabilization term. This is valid only for linear elements. For higher order elements, we need to include the diffusion term into the stabilization term, the integral for the stabilization term. Okay. Now here we have two terms, A dou U by dou x minus F, and once we apply this to both terms, we can write it in this fashion. Okay. So we have A tau A, so tau A square dou W by dou x dou U by dou x minus A tau dou W by dou x multiplied by F. So tau A W by dou W by dou x multiplied by F dx. Now, if we observe this first term, first integral carefully, so here integral from x1 to x2, that is over the element, our two-noded element, tau A square dou W by dou x multiplied by dou U by dou x dx. Now, this is familiar to us. What is this term corresponds to? This term is very similar to the weak form that we draw for the diffusion term, right? So mu dou W by dou x dou U by dou x. Now in place of mu, we have tau A square. So This is a this is very similar to the diffusion term, right? Okay, so thus the stabilization term acts as an additional diffusion with tau a square as the diffusion coefficient. So essentially what we are doing is, by adding the stabilization, we are introducing artificial diffusion into the equation. So this is what we do in any other method, like even if you use finite volume method or finite difference method. So we somehow introduce artificial diffusion to get rid of the spurious oscillations when we solve the advection equation. Okay, so the fundamentally the method is the same in the sense that we add the artificial diffusion. So here the tau a square becomes the artificial diffusion coefficient. Right? Okay. So now we can write the weak form with including stabilization at element level. Okay. So we have all the three terms now. The first two are from the standard, like uh, following the weighted residual statement. This is at the element level. With the first one is for the advection part. The second one is for the diffusion part. Now we have the third term, which is from the stabilization. Okay. And on the right hand side, we have the integral for f followed by the weighted residual statement of the PDE. Okay, starting from the with the residual of the PDE and so on. And then this is the extra stabilization term. Okay, so what we can also call them is, since we are going to use the Relarkin method anyway, that is, we use the same set of basis functions for the solution field U and the test function W. We usually call these two terms as the Relarkin terms. Okay, so on the right hand side, this WF dx, this integral is the Relarkin term, and those terms in blue are the stabilization terms. So this is what we typically call the terms. Okay. Now the element stiffness matrix and force vector. Now once we have the weak form, we can discretize it and then get the element stiffness matrix and force vector. Okay. So here again we substitute for W, we substitute for dou by dou x and so on after discretization, and this is our element stiffness matrix, which is like again nothing much different. The first two terms are exactly same as without stabilization that we have seen in the first part of this lesson, and then we have the added stabilization term. Similarly for Fe, so this is the Relarkin term and this is the stabilization term. Okay. So we have the expressions for the stiffness matrix and the force vector. Next, by using the two-noded element and its basis functions, we find out the closed form expressions for the different integrals in the element stiffness matrix and element force vector. Okay. So I am repeating some of the terms here, but we have already evaluated those terms earlier. So first, let's look at the force vector for the SUPG scheme. So like I said, we have two components. One is from the Relarkin part. So I have denoted it as Fe with subscript G for Relarkin. And this is the same from earlier for the right hand side for the source term for the okay. And here we have the stabilization part. So after substituting the basis functions and carrying out the integral, we get this as the force vector for the stabilization part. Okay, so the total force vector for the element is the sum of the Relarkin part and the stabilization part. Okay, these two terms. We don't need to add them now. Okay, we can implement it directly in the code. Next, we look at the stiffness terms, but here whenever we implement the force terms, always be cautious of the fact that these expressions that we have derived by integrating the basis functions here are valid only for constant f. If f depends on the coordinate, for example, if f is sine of x or some other function of x, then these expressions are not valid. Okay, either you can integrate for the particular expression of x and then come up with the new expressions, or we use gross points. Okay, but here we are going to use only constant f, so these expressions are sufficient for the purpose of this lesson. Right. Okay. So next we are going to look at the stiffness matrix for the SUPG stream. So in this case we have three terms. The first two terms were from the earlier uh, derivation, that is without stabilization, that is by applying the Delafield method. Okay. And the third one is from the stabilization. Okay. The first two parts, diffusion part and advection part, are the same, and we have the stabilization part, and this is exactly like the diffusion term. Okay. Except that we have a different constant here. So instead of mu, we have tau a square. So instead of mu, we have tau a square. Everything else is the same. Tau a square by he, 1 minus 1 minus 1. Okay. Now, okay, with once we have this, we can calculate the total stiffness matrix for each element. Okay. So the total stiffness matrix is the sum of diffusion part, advection part, and the stabilization part. Okay, we put them all together, and then if we add them all and take out the common denominator, and then by multiplying with the factors and okay, and simplifying, we get these four terms for the element stiffness matrix. Okay, so you can take a moment, you can take some time to verify these calculations, like these verify these expressions. Okay. Now, we are going to do exactly same as what we did before. That is, we are going to look at the global stiffness matrix, like somewhere within the within the mesh. For example, if you have a mesh with some n number of nodes, and somewhere within the mesh at an internal node I, and if we take one node to its left and one node to its right, that is, we take three nodes I minus 1, I and I plus 1, same as before. We look at the rows I minus 1, I plus 1, and the columns I minus 1, I and I plus 1. Okay, we look at the 3 by 3 block of the global stiffness matrix. Okay, and this is how it looks like. Now, this is our element stiffness matrix. Okay, so these four terms go into. Okay, first this goes into I minus 1, I minus 1, I minus 1, I minus 1, I. Okay, and then when we assemble for the next element, I plus 1. So this goes into I plus 1, I plus 1, I plus 1, I plus 1, and so on. Similar, okay. So the assembly procedure is exactly the same. So this comes from the element I minus 2, I minus 1, and this term comes from the element I plus 1, I plus 2. Okay, so we are just assembling the element stiffness matrix into the global stiffness matrix. These are the okay. So just this is the I minus 1 row, this is the ith row, this is the I plus 1, and this is the I minus 1 column, this is the I column, sorry, this is the I plus 1 column. Okay, so we are looking, okay, this is I. We're looking at three rows and three columns corresponding to the nodes I minus 1, I and I plus 1. Now, after simplification, okay, we can cancel out this term, Okay, minus AHE plus AHE, and then we can add these two and then simplify everything. Okay, so we get this at the 3 by 3 block. Okay, for the global stiffness matrix. Okay, this is not the full stiffness matrix, it is only a sub block of the global stiffness matrix for rows I minus 1, I plus 1, and columns I minus 1, I plus 1. Okay, we are doing exactly same as what we did before, except that we have one extra term from the stabilization. Okay, we start from this 3 by 3 block. Okay, so this is our 3 by 3 block. Now we are again going to do exactly the same analysis for the matrix to be an M matrix. Okay, that is the off diagonal terms should be less than or equal to 0. Only then we will have smooth solutions. Otherwise, we will get spurious oscillations in the solution. Right? Okay. For the lower diagonal entry, okay, so we have minus of sum of three terms. If A greater than 0, that is if the flow is from left to right, okay, this is our convention, then A is positive. So all the three terms inside the bracket are positive, and we have minus sign multiplying the bracket. Okay, so everything inside the bracket. So this is always negative. Okay, this is always negative irrespective of A, as long as A is positive. So for the lower diagonal entries, so this M matrix condition is satisfied. Okay, now next for the upper diagonal entry, here we have for the upper diagonal entry, so it may or may not satisfy the condition for a matrix, that is less than or equal to 0. So we have again we get condition here. Okay, so minus for this upper diagonal entry to be less than or equal to 0, its numerator should be less than or equal to 0. So minus 2 mu minus 2 tau A square plus AHE, this whole expression, okay, should be less than or equal to 0. And from this, we can derive the condition for HE. So the HE element length should be less than or equal to this expression in order for the matrix to be, the stiffness matrix to be an M matrix. Okay, so what does this imply? If we again take the same condition, same case as before, that is, we take A equal to 1, and for a diffusion coefficient of 0.05, we calculate HE, okay, from this expression. So we substitute the parameters, and HE is, it should be less than or equal to 0.1 plus 2 tau. Now, remember from earlier, when we had no stabilization, that is when this term didn't exist, we had only HE should be less than or equal to 0.1. And we have verified it with the code as well. Right? Okay. So now we have an extra term, 2 tau. For any tau greater than 0, okay, so 0.1 plus 2 tau is always greater than 0.1. So that means the mesh size that we need, the element size that we need can be higher. Okay, so it's going to be higher. So that means we can use a coarser mesh when compared with the like naive formulation, that is without stabilization. Okay, so by adding the stabilization, we are lowering the requirements on mesh size, the element size. That is, we can use a coarser mesh to get smooth solutions by getting rid of spurious oscillations. Okay, so this is the advantage of adding stabilizations. Okay, So now the big question is, what is the stabilization parameter? What should be the stabilization parameter? Now, by looking at this expression, we can, and by looking at this condition, we can see what should be the stabilization parameter. Okay, that's one way of looking at it. And we have to choose the stabilization parameter such that the stabilization parameter tau vanishes, that is, it goes to zero as we refine the mesh. We know that if we use sufficiently fine mesh, we get rid of spurious oscillations. So if we were to use sufficiently fine mesh, then the stabilization should have no effect. So we have to we have to devise the stabilization parameter tau such that it goes to zero as the element size goes to zero. Okay, so we can derive a simpler one by looking at the condition for the M matrix. So this is the numerator of the upper diagonal term, upper diagonal entry. Okay, so this is the condition. Now by rearrange this for tau. Okay, so we take this 2 tau a square to the right hand side. So then we have 2 tau a square should be greater than or equal to AHE minus 2 mu. Okay, and then by taking 2 a square into the denominator on the right hand side, we get tau should be greater than or equal to AHE minus 2 mu divided by 2 a square. Okay, now we distribute, okay, we separate the terms. So we cancel 1a, so HE by 2a minus mu by a square. Okay. Now, if you observe carefully, so for mu non-zero, okay, so He by 2a, sorry, for mu non-zero, what, uh, okay, so whether mu is 0 or not, okay, so let's see what we can do. So we can take tau He by 2a. Okay, so this is, so tau should be greater than or equal to He by 2a minus mu by a square. Now, if we take tau as He by 2a, this condition is satisfied. If mu is 0, then we have exact condition, right? Tau equal to He by 2a. If mu is greater than 0, then He by 2a minus mu by a square, it is going to be less than He by 2a. So He by 2a is always higher than He by 2a minus mu by a square for any non-zero mu. So by taking a tau equal to He by 2a, we satisfy this condition, and we always have a, an half diagonal entry that is either 0 or negative. Okay, so this is the condition that we derive by following the entries in the element stiffness matrix. Okay, once we know the element size and once we know the advection velocity, we can calculate the stabilization parameter, and then we can calculate the element stiffness matrix, element force vector, assemble them, and solve the problem. Okay, that we will do in a few minutes. There are also more complicated expressions for tau. Okay, for example, this is like for this gives second order accuracy, and it also includes, okay, the diffusion term, okay, in a much more like, okay, so we have a much better contribution here in the, okay, so this again, this is derived by following the function analysis for optimal convergence and all. Okay, and there we can also derive by following the finite difference method. Okay, so for the derivation of finite difference method and, okay, and other aspects, we can refer to this test book. Okay, so about how we define, sorry, how we derive the stabilization parameters. Okay, so in this test book, follow chapter 2. Okay, this is the test book by Donia and Huerta. So follow chapter 2 in this test book for the details on the stabilization parameters and how we can derive the optimal value. Okay. So the optimum value is tau equal to beta AHE by 2, where beta is a parameter. Okay, so it depends on the petlet number, the element petlet number PH. PH is AHE by 2U. Okay, and beta varies between 0 and 1. Okay. So this is the plot of log 10 of petlet number and versus beta. So for very small value of petlet number, that is when diffusion is not dominating, beta is almost 0, uh, which is what we need. Okay, so we don't want any stabilization for diffusion dominated problems because the matrix is already an M matrix. We don't have any spurious oscillation issues. And when petlet number is very high, so beta goes to 1, and we do have tau equal to AHE by 2. Okay, this is again very similar to HE by 2A. Okay, so just like they differ by a constant multiple, otherwise they're almost the same. Okay, now for more details about the stabilization parameters, refer to the textbook and also the references, and there are also a lot of papers published by Professor Tom Hughes, Professor Ted Dewar, and also Professor Codina. Okay, so next let's implement this stabilization method in our code. So we don't need to start from scratch. We have already implemented this for FE formulation for advection diffusion equation. Okay, all we need to do is we add the stabilization term. Okay, we have the diffusion part, we have the advection part. Okay, next we add the stabilization part. Okay, so let's denote it as Ks. Okay, this is tau A square divided by HE. Okay, so our stiffness matrix tau A square by HE multiplied by 1 minus 1 minus 1. Okay, then we add this to a stiffness matrix. And then, so this is our Delarkin term and stabilization. Okay, tau AF minus 1 plus 1. Okay, minus 1 plus 1 tau AF. And our element force vector is Fg plus Fs. So Delarkin part plus stabilization part. Okay. So and afterwards we don't need to change anything much. Now what all we need to do is we need to calculate the stabilization parameter tau. Tau equal to, so let's use the simplest one we have, HE by 2A. HE by 2A. Okay. Now when we ran this code earlier, we had spurious oscillations. That is okay. So what we can do? So we can make tau 0. That is, we are nullifying the effect of stabilization. Okay. So we get spurious oscillations. Now, if we include the stabilization, you can see we got rid of the spurious oscillations. Now, the solution has no spurious oscillations, which is not accurate, but we got rid of the spurious oscillations. Now, our solution should improve as we refine the mesh. Okay, so let's say 100 elements. Okay, so the solution has improved, but it is still not accurate. So that means we need to use more and more elements. So 1000 elements. Okay, so as we include more elements, the solution has improved. It matches well. Okay, so that discrepancy is because when we plotted, we have taken only 100 points. So now if I change it to 1000, the matching should be better. Okay, so again, still like okay, so there is still some error. Okay, so that is because the stabilization parameter is too much. We are adding more diffusion, so the solution is bit much more smoother than it should be. Okay, how can we improve? So one way is use a different stabilization parameter. So let's take the optimal value. Okay, so first for this, first we need the element platelet number. So AHE by 2 mu, AHE divided by 2 mu, and then we need to calculate beta. Beta is dot PE minus 1.0 by PE, and tau is beta multiplied by AHE by 2. AHE by 2. Okay, let's go back to 100 elements. Okay, now when we use HE by 2A as the simulation parameter, there was some error. Now with this optimal value, now the solution has improved, right? So if you want, we can check later. So let me recommend this. We use HE by 2A as the stabilization parameter. So the solution has some discrepancy. No oscillations, but the solution doesn't match. That means the stabilization parameter is not good enough. So what we are going to do, we are going to use the optimal version of the stabilization parameter. Okay, now we get a good match. No oscillations and better result. Okay, and we can, so if we reduce the diffusion provision further, we need even finer mesh, but using the stabilization formulation, we get no oscillations. So and we can let's reduce the number of elements and see. Okay, so as you can notice, so this optimal stabilization parameter gives more results with more accuracy. And we can also check the entries of the global stiffness matrix. Okay, as you can see, so in the lower diagonal, the values are -1, and in the upper diagonal, the value is 0, which is what we need for the matrix to be an M matrix. Okay, so this is how we solve the problem of spurious oscillations when solving the advection diffusion equation using finite element method. Okay, now what is happening here? Okay. So we have added the stabilization term, we have calculated the stabilization parameter, and we do have optimal value. And this optimal value, remember, is only valid for the two noded element in one dimension. Okay, if we go to two dimensions, then it's very difficult to derive these optimal values. But we do have some expressions that we can use that give us like better results. We look at those expressions when we go to 2D problems. Okay, so now we have completed 2D. Now, why do we get better results when we add stabilization? What is happening? To understand this, first let's try to understand these terms in SUPG. So first let's look at a PG. So this is our weak form. Okay, by ignoring the diffusion. For the time being, let's ignore the diffusion term because advection term is the main culprit. Advection term is the problematic term. Okay, we look at only the advection term. Okay, so by ignoring the diffusion term, this is the weak form for the SUPG method. Okay, including the stabilization terms. Now, what we can do, we can combine these two. Okay, and before we do that, let's okay. Okay, so we can combine these two. We have the same integral and we can take dou u by dou x and a from both the expressions as a common factor. And then from the first term we have w, and then from here we get tau a dou w by dou x. So we put that in the bracket. So we are just merging these two. And similarly, we are merging these two by taking the common factors. Here the common factor is f. Okay, so we have w plus tau a dou w by dou x. Now, if you notice here, inside the bracket, we have the same expression on the left and right hand side. Okay, now we can denote this as an effective weight function. Okay, so for example, like let's say we are starting with our PDE dou u by dou x minus f. Okay, dou u by dou x equal to f. This is our PDE. This is the pure advection equation. As I said, we are ignoring the diffuser term. So okay, so dou u by dou u by dou x equal to f. This is our PDE. And if we take w plus tau a dou w by dou x at the weight function, this is the weak form. Okay, so for the discussion, let us denote this as w bar. Okay, so then our w bar is the weight function. Okay, so now when w bar is the weight function, we can no longer take the same basis functions for u and w bar. We have the same basis functions for u and w, but the basis functions for u and w bar are not the same. Okay, so this is okay. We no longer have the same basis functions for u and w bar. Now this is not the Delaunay method anymore. In the Delaunay method, we take the same basis functions for the solution field and the test function. But in this case, it is not the criteria, it is not satisfied. So what we now have is the Petrov-Delaunay method. In the Petrov-Delaunay method, the basis functions for the test function and the solution can be different. Okay, that is the difference between Delaunay and Petrov-Delaunay method. So that okay, so this is why it is called SUPG. PG is Petrov-Delaunay to state the fact that we are not using the same basis function for the solution field and the test function, the effective test function. Okay, remember it. We are not talking about W. We are talking about W plus tau a dou u by dou x because we have the added stabilization. This is the PG part. Okay, what about the SU part? No. Okay, again we have the weak form for the stabilization with stabilization, that is the Petrov-Delaunay form, and by using the discretization we can write it in terms of okay and okay, so I'm missing u here, okay, but please ignore it for the time being. Okay, so there should be an u here. Okay, so but for the time being, let's ignore it. Now we have this discretized form and we know the basis functions for our two noded element n1 n2 in terms of x1 x2 and x1, and from n1 n2 we can find the derivatives. These are the derivatives. So from this we can calculate the term inside the bracket n transpose plus tau A dou n1 dou n by dou x transpose. So that is, so we add this extra terms to n1 and n2. So that which are n1 plus tau A dou n1 by dou x. And we know that dou n1 by dou x is minus 1 by he. So we have n1 minus tau A by he. Similarly, for n2, n plus tau A dou n2 by dou x. Dou n2 by dou x is 1 by he. So n2 plus tau A by he. Okay. So when compared with the original basis function n1 and n2, we have new basis function n1 minus tau A by he, n2 plus tau A by he. Okay. Let's plot them. Okay. So these are our original basis functions n1, n2. n1 is 1 at h1, n2 is 1 at h2, and zeros at the other nodes. Now, let's plot this n1 minus tau A by he, n2 plus tau A by he. Okay. So this is our flow direction from left to right. So A is positive, and we have our n1 and n2, the original basis functions. And then we have n1 minus tau A by he. Since we are subtracting some positive value from n1, we get its value is lower. So this is our new basis function n1 minus tau A by he. And for n2, we are adding some positive value, so its value will be increased. So n2 plus tau A by he will be above n2 by this amount, tau A by he. So this is n2 plus tau A by he. Now, okay, so these are the plots of the new basis functions. So what exactly is happening here? So in order to understand, let's put one more element to the right side of h2. So we have like h1, h2, h3. Okay, so we have three nodes. And then let's plot the basis functions for both elements. Okay, so we have n2, and then for the next element, we have n1. And then, okay, so n2, n1 are our Delaunay basis functions from the Delaunay method. And then on top of this, we have n1 minus tau A by he and n2 plus tau A by he. Note, we still have the other two basis functions here. I just haven't plotted them, like for the sake of clarity. Okay. Now, what is happening? Okay. So now if you look carefully, so with the stabilization, we have an increased contribution to the basis function on the upstream. And we have reduced the contribution to the basis functions on the downstream. So this is like we are upwinding. Okay. So by adding the stabilization term, we are creating the effect of upwinding. Okay. If you follow from finite difference method or finite volume method, so this is exactly what we are doing. So we are creating a streamline upwinding by introducing the stabilization term to the weak form. Okay, so this is the SU part in the SUPG method. I hope I made it clear. Okay, if you have any questions, please post in the comment section, and I will also share the codes for you to follow. Okay, again, okay, you go back here. You can play with you can play with mesh sizes. You can play with stabilization parameters. You can look at the global stiffness matrix. Okay, you can change the value of mu, you can change the value of A and see how it affects the solution. Okay, so thank you. See you in the next lesson.